Hi, my name is Daniel Isaacson, and this is my brushed DC motor presentation. This project was completed for ET350, also known as motors, at the California State University Maritime Academy, and wouldn't have been possible without IRA funding and supplying each student with a 3D printer, which allowed for this project to be completed virtually during the COVID-19 pandemic. A quick overview of this presentation. We're going to start with the construction of a brushed DC motor, as well as my personal construction. We're going to move on to a demonstration of my motor. Following that, we're going to move on to the performance statistics of my motor. And following that, we're going to move on to the electromagnetic diagrams and the theory behind creating my motor. Fifth is the CAD drawing of my motor and its custom parts. Sixth, a slideshow of the manufacturing assembly processes. Seventh, we're going to talk about future improvements I plan on making to my motor. Eighth, I'm going to talk about my experiences and reflect on this semester in ET350 and finish off with acknowledgements and a big thank you to everyone who supported me during this class. My motor is made out of four basic parts. First, we have our end cap, followed by our spacers, rotor, and our stator housing. The stator is comprised of the spacers, stator housing, and the end cap, whereas the rotor is internal to those components. Here's a depiction of the basic construction of a brushed DC motor. We have four main parts. We have our commutator, our brushes, our armature, and our magnets. Our commutator is what is made up of several sections that are connected to each individual wrap or armature. We have our brushes, which supply our commutator and our armature with current. And we have our magnets that create a magnetic field, a B field in a certain direction. That B field always moves from north to south. When we have current running through our armature, that also creates an opposing current, and that is what rotates our armature, or in my case, our rotor. Before we start with the demo, I'd like to make all safety features apparent. We have ratchet strapped the motor 42 inches above the ground, and as you can see, I'll be wearing safety glasses as well as standing 2 feet away from the motor with a momentary switch in hand. We will be measuring the distance traveled using the measuring tape located on the ground. Now let's go ahead and watch this motor run. As you can see, it landed on the furthest piece of tape. After a couple of tries, I ended with my final distance. Now here's the side view of my motor hitting the ball. Now it's the moment we've all been waiting for, the performance values associated with my motor. My overall weight was 1.4 kilograms, or for those of you who aren't metrically inclined, around 3.08 pounds, roughly the amount of weight of 9 apples. And the distance traveled was 4.5 meters, or roughly 14.75 feet. Now, this was a huge distance for me, as it surpassed that of my expectations. I wasn't expecting my motor to hit any further than 6 feet. And when I hit it, my 14.75 feet, I was astonished and proud of myself of all the hard work that I've put in this semester. Now it's time to go into the theory behind the creation of my motor. My motor uses an alternating 6-magnet design with 3 coils. As you can see, we have alternating north-south magnets, as well as a red coil, a yellow coil, and a blue coil. Current is being supplied to those coils all at the same time through our brushes located with the positive and the negative sign. When you see the X, that's when you know that current is flowing into that wire. When you see a dot, that's when current is flowing out of that wire. Also, we have our purple arrows that are depicting our magnetic fields always going from north to south. Now, if you use your right-hand rule and the Lorentz force, you can always depict that we're moving counterclockwise. In the second diagram, we have our magnetic field, we have our coils. However, we are not supplying current to our coils at this time. With that pink arrow, we see that the brushes are actually being supplying current to the insulated section of our commutator. So no Lorentz force is created, and at this moment, our motor is not spinning. Here we have the CAD drawing of my motor, and we can see in that drawing that it satisfies all requirements, meaning that the diameter of my motor must not exceed 5 inches, and the length of my motor must not exceed 5 inches. Here we have 3 specific parts that I had to design in CAD. First, on the far left, we have our brush holder. This was mounted onto my end cap and allowed for a specific place where my brushes would sit so there would be no movement. Also, here's our spacers that is seen in between our end cap and our stator housing, as well as our rotor and my design for the rotor. Now onto my favorite part, it's an assembly manufacturing slideshow. Here we just have a failed print due to a leveling error. We have version 1 rotor and some test prints for tolerances, bearing, and all thread. This is my final stator housing being printed. There it is completed. Here we have final end cap, final stator housing. We have the final competition bat. We have the final end cap, stator housing, and spacers. We have version 1 wrapped rotor. This one unfortunately severed all of the coils due to the rotor not being epoxied onto the shaft. So unfortunately, all those wraps were destroyed, and those were my wraps and how perfectly in my packing factor and how everything was so nicely laid out before I epoxied, and they were destroyed. There, after I destroyed all my wraps, had to epoxy them, epoxy my rotor onto the shaft, and started again. And as you can see, I kept with my same process, using a dowel and a wire on the dowel to get my coils just perfect and packing factor high. Everything's completed here. This is my final rotor. As you can see, I labeled every terminal, wire terminal, either with a positive or negative, knowing where I was going to connect them onto the commutator. And here we go with the final assembly here of all the parts, pre-rotor wrap. And there is the final assembly. Everything's looking good. We have our terminals, our brush terminals wired up. And as you can see, everything looks good. You can see the commutator soldered together. The bat is attached. And there's a close-up view of my wires and my commutator, my brush sections. There we go again. You can see how A, B, and C positive leads were shorted together, and C, B, and A negative terminals were shorted together. So I was supplying current to all 3 sections, all 3 coils of wire at once. Some future improvements and design elements that I plan on incorporating into my motor are a base plate. Because of this rounded bottom, I want a flat plate so I can mount it way easier. And I've actually already printed this design, and this is what it looks like, and it attaches right here to give the motor a flat base to mount onto something. The next print I will be conducting is a U-bracket that would go over these spacers that allow for me to mount this so all force generated by this motor isn't wasted in moving around the motor, but it's actually directed out of the shaft and into the bat, so potentially I could hit the ball even further. This semester came with a lot of new experiences, and the 2 most prominent experiences that I had this semester were actually learning how to use CAD software, specifically Autodesk Fusion 360, and I became very good at designing my own pieces and ultimately finishing my motor on Fusion 360, as well as learning how to 3D print. This was the biggest takeaway I had this semester, and it actually led me to purchase my own for personal creations. And I feel like this is something that I'm going to keep with me forever. Passion for 3D printing and design that I didn't have before my ET350 Motors project. I want to give a special big thank you to everyone that made this project happen, specifically Professor Cheng Su and Professor Clyde. You guys were there since the beginning. You guys made it work. You guys didn't let us down, and we went through with our project, which was awesome. Also to the engineering technology department, all the staff and faculty were willing to help us in every problem that came up. Makerspace staff, ordering and supplying us with all the tools necessary to complete and assemble our projects, and the fellow cadets who didn't give up and supported one another given the pandemic and everything that was going on. Thank you for watching my video.